right, it looks like everyone's back, so let's continue. Like I said, today I'm kind of closing up some loose ends, so I'm just we'll go through this basically this simplified shading model that we had at the beginning, and also in the book. When you look in the book, there are the simplified shading model was at the beginning in relation to ray tracing, although it is of course the same basic concept for perspective projection, as you have seen, of course, in the practicals. Also in the book, then there is a second chapter, so I'm doing it actually in the same way as in the book. I have a simple version first and then a more detailed version at the end. The reason why I'm mentioning this is not only to recommend that you also look up this chapter 4 again in the book when you repeat the lecture, but also because the book uses a different notation in both chapters, and that can of course be a little confusing, and that's why I decided now to stick with the notation of chapter 10. So a couple of things that you see now might look new and strange to you, but are actually exactly the same as what you've already seen, I think, in the second or third lecture. So just be careful with this, but it actually can also sometimes help quite a lot, or sometimes I find it also quite nice when I have the same thing represented in slightly different ways, and at first I'm confused, and then I look into it and then I see, okay, here is the relation, and they just write it a little bit different, and then it helps me understanding it a little bit better. So it can also be beneficial, just be careful. Good. So yeah, we said that we already had this diffuse lighting with the Lambertian shading, and I hope you remember that this Lambertian shading is where we say that the intensity of light depends on the direction of the light, and we saw that it depends on actually the angle that the incoming vector has with the normal vector, and that is called Lamberts cosine law, which says that the color that we perceive at the point, or the influence of the light on the color that we perceive on a point, depends on the angle at which that light reaches the surface, and then of course the angle with respect to the orientation of the surface, which we usually measure with the normal vector. And of course, since we remember the scalar product, we also know that the scalar product can be written as the cosine times the length of the two vectors, the cosine of the angle between the two vectors times the length of the two vectors. And if we have unit vectors, then this is 1, and then of course we can also say, instead of proportional to the cosine, we are proportional to the scalar product, which of course we can calculate without a trigonometric function, without actually knowing the angle, just by knowing the two vectors. So this is much easier to calculate, and because we have unit vectors, it is the very same. So it's another example for a situation where it comes in very handy to have these unit vectors. Good. And yeah, so this is one of the things that we didn't mention at the beginning, because at the beginning we were just talking about vectors and coordinate systems, and we talked about they are different, but we did not really give a concrete reason for it, or concrete motivation. And now of course we have the camera system, we have world coordinate system, and of course we should also know that these transformations do not always preserve the normals in an appropriate way, which is why usually this calculation should be done in the world coordinates, because otherwise we have problems with normals. Good. The other thing we discussed already is of course that this diffuse light, that it depends on the direction of the light. So it depends if we have, for example, a light source here, like a lamp, supposed to look like a lamp. If we move that, of course, in this direction, then the left and right, then the direction changes, but it doesn't depend on the location. So if we move it a little closer or a little further away, it doesn't usually change the influence of the light. Of course, that is all kinds of light models that we have here are of course simplifications, but in general we assume that this kind of light does not change does not depend on the location, in contrast to, for example, a spotlight that you're supposed to implement now as part of the practicals. Good. And then of course we can use this to model the light, this Lambertian cosine law, to model the light by saying we take the scalar product and multiply it then with the color value of the surface, which is expressed by this so-called diffuse reflectance value. So that is related to the surface, the color of the surface, but also of course multiplied with the color of the light, because if, like for example, a red light shines on a surface, of course it looks different than if a white light shines on the surface. So the light source is also considered, and that is modeled by an active factor, which is usually called the RGB intensity term. And then we just multiply it with the cosine, because this with the scalar product, because that is the same then as the cosine. And of course I hope you also remember that we are the scalar product can, of course, because it depends on the cosine can get negative, that we have to do the maximum here of 0 and the scalar product, and that way we guarantee that we either have 0 or positive values, because of course the negative from a geometric interpretation would mean that the light source is behind the surface, so of course it shines on the surface, but we don't see it from that position because we're looking at it from a different side. Good. Yeah, of course, that's I already had it explained. I just summarized it here. So you see a lot of repetition now, but I think it's also good and nice to recap the stuff, especially from the beginning where we had a lot of material, and I'm pretty sure a lot of people were kind of overwhelmed. But I hope now when you see it again that you're kind of like, oh yeah, it's actually not that hard and not that difficult. Good. Another thing we didn't really talk about is, of course, we need the normals for the reflection to calculate the light influence. But if we have objects, of course, then we said that the normal vectors are not always defined at the borders of these. So, for example, here for the cube, we have normals on the surface pointing in this direction, on the side pointing in this direction. But what do we have here at the corners or at the vertex here? Because here we basically have two. No, we have no normal, because the normal at this position is not defined, but we have two normals from the two surfaces, so we could take both of them. And the answer to the question, what are we doing, is really, there is no clear answer, because there are certain options that we have, and each has, of course, a different characteristic, and we can, of course, depending on the situation that we have and the model that we have and the scene that we're modeling, one approach might in a certain situation be better than another one. So, for example, if we have a cube, then of course we have strict color changes here. Then of course the easiest thing is to just, between these two, just take one of them and throw one away, and then just make one the dominant one. So just this side just becomes then at maximum 1 pixel wider. But other than that, since you have a sharp changing color here anyhow, it doesn't really matter, so you can just take one of those. If you have a more smoother change of color than if you just take one, of course, you could say you probably want to interpolate between the two, but of course if the colors are very different and you interpolate with them, you can also kind of get a little artifact that it looks like a little stripe here, because you see that it's just an intermediate color between these two colors here, if you, for example, do not interpolate the triangles. And that's also then, of course, you can also say I'm not just interpolating this one, but I'm also interpolating the whole triangles here. And you see this is actually kind of similar to what we had with the bump mapping, where we said that we're interpolating them to create the illusion of a certain geometric shape, in the same way as, of course, we can do it here. It's basically the same idea, to interpolate the normal values in a way that we get here a smoother transition about this rather rough corner. Good. Yeah. And in addition to this, or one of the problems here, of course, is, like we said, when we are behind it, then of course it gets negative. The light gets, the cosine gets negative, so we don't have the light here. So what we do is we, but of course, in reality, we often have just because there is no direct light doesn't mean the scene is completely black, and because the light also reflects with this, and of course, you can calculate these reflections, but this is very complicated. We will actually see in the next lecture one approach to do this, how we can consider this reflectance of lights in a way that also spots that are usually completely in the dark are lighted. And this is called radiosity, and we'll talk about this in the next lecture. But of course, we also talked about it before, where just applying a trick, which is just adding a constant factor to all color values or to all points, and basically have this standard light everywhere, which is then we called the ambient light, which you see here. This is, again, it's the same formula as before, just with different letters here used here. The ambient light, it's not drawn here because it is anywhere, so I can write it here, but it doesn't point anywhere because it is everywhere. which means it is also at that point, which means, of course, it influences the diffuse reflectance, because that is the light that always shines on all points. And if this it also, but it of course is independent of the light that shines here, because that light is an active light source, like the ambient light is then also an active light source. So and then of course we see, of course, if the light is zero, if this scalar product is zero, we still have the diffuse reflectance times then this ambient light. So that was a cheap trick to do it, and it works quite well usually. Another trick to do this is, of course, we could also put a dim light source at the eye position, and then of course we can be sure that every spot we are looking at in the image has at least a little bit of light, because we are shining so bright to make the light to spot. Good, yeah, so you see a lot of tricks and hacks we can do to make some nice images, some nice shadings and colors there. But of course, the problem with all these diffuse light is that it doesn't consider the specular reflection, and we already talked about how to solve this with the so-called Phong reflection. And I think you also implement that in the practicals, right? Yeah. One of the things here is, of course, that the viewing direction matters. So the reflection, we said that the reflection is maximized when we are looking directly at the surface in the same angle as the surface hits the as the light hits the surface with respect to this normal vector. So at this position where the eye vector is the same as this so-called reflectance vector, which is the vector that reflects at the same angle with respect to the normal and the incoming light, then we have a point of the maximum brightness, and the more we move away from it, the more the light or this brightness spot decreases. And of course, a smooth decrease can always be modeled very well with, for example, trigonometric functions. So again, we're using the cosine here to model this. So we use the scalar product of the eye vector with this direction, a reflection vector. And then, of course, we start with the maximum if their angle is 0, which is the cosine of 1. And then the larger it gets, the larger the cosine gets, the larger the angle gets, the lower the cosine gets, till we reach an angle of 90 degrees, and then we have zero reflectance. But of course, that would only create one very specific spot, which is why we said we can introduce this so-called Phong exponent that gives us a way to kind of manipulate this decrease in brightness, or increase the decrease in brightness, to delay it or to make it faster, and that way to have like bigger and smaller spots like you see it here in the image. And of course, also when we do it in the actual calculation, we have to consider that this scalar product can get negative, so we have to take the maximum of these two, the maximum of 0 and the scalar product. And to deal with the situation that the light might actually be negative. Now, what I was saying before, when the light was negative, I was already wondering if someone would raise their hand and say, well, but isn't there another case that doesn't work? Because there is actually a case where there are actually cases where you can have a negative scalar product, but you're not behind the object. So for example, in this image that I illustrated here, if they are further away than 90 degrees, then of course you have a scalar product that is larger, that is negative, and that's why, of course, then the color with the Phong shading model would give you a 0, which might not be that critical, because you see here it's only when you're looking at the reflection at an angle larger than 90 degrees, which would in reality also be not very bright. But nevertheless, it is not really correct, which is why sometimes we are also, or which is one of the reasons why we're sometimes using this so-called the modification of the Phong model, which is the blind Phong model, which does not use the reflectance vector, but this halfway vector in between the eye vector and the light vector. So we're not using the reflection vector, but we're looking at the vector that is directly between the eye and the light. And that vector, of course, that can be very easily calculated. I already had this in a third lecture, but I didn't write the calculation down. But of course, it's very easy. But it's I put it down now to illustrate. It's another example where it comes in very handy to have unit vectors, because of course then we can just take the average can just add them up and divide it by the length, and then we have the h vector. Of course, if you don't know why we need unit vectors here, look at the image and try to understand it. So that's should be clear. And then of course we see that we basically have the same situation here than before, that we get a maximum if this halfway vector is in line now with the normal vector, not with the I vector of course, but with the normal vector. But we also see that no matter how we place the light and the I source here, if we have this situation here, the furthest we can go away with the I is very close to the line, to the surface here, and the furthest we can go away with the light is very close to the surface here. But in any case, the H vector will always be positive, so it will never be negative. So we will have always we will never run into this problem with the negative values here. Good. Now now we talked about how to do this row shading, how we can calculate this very efficiently. And now we said, okay, the func shading doesn't work with it, so we have to do a special calculation with it. But of course we want to integrate the two things with each other, and of course the Gros shading eliminates all bright spots because it does this linear interpolation. But what we can do is, of course, we can take the normals and can interpolate with the normals, like we did in the same way as we interpolated the color values. We can also interpolate the normals. One way would be with the scanline approach. Another way that they mention in the book would be with the barycentric coordinates. Like I said, the book doesn't use the scanline algorithm, which is of course why they also not use it for the normals here. But the reason why I'm bringing this up here is that the book uses a different notations of the barycentric coordinates, which I didn't use for the triangles, because I think the way I did it is more intuitive for the triangles, where we do this intersection test. But here for the interpolation, actually, I think the book version might be more intuitive. And like I said, sometimes it's very helpful to look at if there are different ways to represent the very same thing. It can be very helpful for your understanding to look at them and try to figure out why are they the same and how do they really relate. So this is why I want to bring this up here. So the way they do it in the book is they have three vectors, and they do the barycentric coordinates by giving each vector a constant factor, a variable factor, and then by manipulating those factors, they can, for example, do intersection tests or do coloring of triangles in the same way as we did it, but we only had two factors and we subtracted two vertices of the triangles from each other. And the reason was, of course, like I have it here in the image, if you have the three vertices of a triangle and then you subtract them, then you get something here which is similar to like a coordinate system with this little twisted grid where you have parallelograms as grid cells. So you can think about this here is, if you have here your gamma and here your beta, then this is basically like a plane, and you can, or a 2D subspace which has a different angle than 90 degrees, but it's just a parallelograms style grid that you can address then all the points here, and that you can also easily check if it is within that part here that represents the triangle. And you can also use it easily use it for interpolation, because we saw that for beta and gamma is 0, we are here, and if we increase gamma to 1, we will end up here. If we increase beta from 0 to 1, we will end up here. So we also saw that this is also very good for linear interpolation. But of course, if we have here normal vectors and we want to interpolate between them, then this notion might not seem that intuitive. It might seem more intuitive to really have the three values there and then have a weight for each of the values. And we see here on the right side that is really actually exactly the same representation. If we take the one that we had and then just solve these brackets here, so we put the beta in here, we have beta times the vector b, minus beta times the vector a, and then we combine all the a values, we get this factor here. And if this factor is our value alpha, then we have exactly the same representation, and the same representation that they use in the book. So this is, you see here, a very simple transformation that illustrates that these are really exactly the same, and depending on what we are doing, it might be more intuitive to write it one way or the other. Of course, also be careful that with this, then the condition changes, but I'll leave this as an exercise for yourself to check why this is a condition for a point triangle intersection test. We will actually do more about these intersection tests when we talk about ray tracing later. Good, and then of course we can combine all of these together. We already had this for multiple light sources, and you already did a lot of these also in the practicals, or will do more of this in the practicals. There is also here another modification that I took from the book, that we can also add another term here that allows us to do some further modification with the Phong shading. So in general, there are a lot of modifications here that we could do. In general, especially when it comes to shading and lighting, there are a lot of modifications and a lot of tricks to try to create better images. I found it quite nice in the book, in the FAQ section at the end of these chapters. The first question here was something like, aren't some of these approaches just a hack? And I think I said this the same already a little bit with respect to proline noise. There is very often you look at an algorithm and it's really or an approach, and they really put something in, you really think, yeah, this really looks like a hack. But that's why I'm always trying to go a little behind it and explain what is the idea behind it and what characteristics are changing when we, for example, modify this vector in a certain way. And that kind of always sometimes illustrates why this is, even if it is a hack, a very good hack that really creates a good effect. Good, so there are many more things that we could do with shadings, but I want to stop it here because also the more advanced stuff is also not covered in the basic chapters in the book, but more in the advanced chapters. So if you want to, you're very welcome to look into that. And of course, you are partly not only welcome, but forced to look into that as part of the practicals, where you're supposed to work on spotlights and coctorants, for example. But for the lecture now, this closes this pipeline part. And like I said already, next time we will talk more about a global illumination approach and talk a little bit about shadows. So this is not in the book next time, but I have additional material references that I can give you. And then we will finish up by ray tracing. So just a little recap, because now we have really finished up all the basic stuff from the book. We have even already done some parts of the advanced stuff. The only thing I did not cover was this chapter 9, and I will not cover that because it's about signal processing. So that is a little bit off from the content. It's important and interesting, but it's not really, doesn't really fit very well to the other stuff, which is why I'm skipping it in the course. And also I skipped at the very beginning this part about raster images that I already mentioned. So the only thing that we didn't cover from the basic sets is the rest of chapter 4 with the ray tracing, which we will do then in the end, like I said. Good. So are there any questions? Yeah, so today is a little shorter, like I said, because we're wrapping up things. One final comment. The tutorial, we've seen that the number of students dropped. Let me remind you that this is a very bad idea not to go to the tutorials. I think it's very helpful for you to go there. But of course, if the number drops, there is no point in having the people in 2 half or more than half empty rooms. It makes more sense to have everyone in one room, because then we can have 2 TAs there so they can react quicker if there are more questions at the same time. Which is why I would like to ask you, if you go to the tutorial, start filling up from room 201. If it gets too full, then we can go to the second room as well. But if there are not enough people there, if we all fit in one room, then it makes more sense to start there. Good. So, any more questions? No? Then see you again on Tuesday.